All right, so we're recording the class as of now because we'll get started on the first chapter here pretty soon. And so that's class videos. Remember to email me before class, a good hour before class or more, because if you email me closer to class time, I have a tendency to be working on things and not checking my email. So let's see, where were we? Labs, professionalism. This is another placeholder just for me to enter your scores. So you don't need to do anything with the labs or professionalism here. The due dates don't mean anything. They're just there for my use. And then you have your course syllabus, and then the OpenStax physics textbook. So this link takes you to the textbook for the course, which is from Rice University. Rice University started this publishing house called OpenStax CNX. And they are what is called a copylefted institution. If you've heard of copyright, I'm sure, whereas when you write something, you have the right to its to selling it and the right to its distribution thing and all that stuff. They call this a copyleft because they're allowing anybody to use it and distribute it as long as they don't sell it. So nobody can sell it, but anybody can use it and change it if they want to even. So this book is their college physics book. Sometimes when you open this, you'll get a little thing up here that says there's a newer version of this book and you can switch to it. And it's always good to use the newest version. Over here, you've got your little contents button that shows you all the different chapters in the book. Useful. At the end of the book, they've got some appendices that are full of information that we will often use in this class. You can also use the search bar up here, which I think is extremely useful, probably the most useful feature in this book, so that you can find something immediately. Let's say that I'm looking for Einstein's postulates. So I put an Einstein postulate here, and I hit the search button, and it thinks about it for a little while. Wow, its website's slow today. And it takes us to chapter 28, special relativity. And it shows us all the different places where Einstein's postulates are talked about, also in chapter 34. So, very useful feature, probably the fastest way to find something in your textbook. It's a good thing to remember because my exams are open book. So if you want to find something very quickly during an exam, I highly recommend you don't go to the table of contents, find the right chapter, and start flipping through the book. That's a waste of time. Search the book, find the thing you're looking for, and go right to it. So the search feature is extremely important. Then we have over here, we have our little get this book button. You can download it as a PDF so that you have it, you don't have to use it online. You can just have it on your computer all the time. Or you can download it as a zip file and then unzip it and use it from there, whatever. Also, you can buy this book. Like I said, I can't remember. I think you have to go to OpenStax CNX to actually buy the books. So let's go here to, so we're doing college physics, not university physics. College physics is the algebra-based book here. And then we go to the, oh, that's not right. That didn't help. OpenStax, give, support. I'm not sure where to buy them now. Let's go find out. Buy OpenStax printed. Here we go. No. That's not. OpenStax. Well, you can buy them at a lot of different places, apparently. I thought they had their own place where you could actually buy them, but apparently they don't. So you can buy them at Amazon. So at Amazon you can buy them. Looks like physics is going to cost you, college physics is, holy crap, $3,000. That's not right. They have the Kindle edition though. The hardcover for $3,000. That's a problem. It's not going to work out. Somebody's got to have it here. It looks like the university physics one is 35, so here's the college physics for 36. So that's not bad at all. So for a textbook binding, to rent it is 29. To buy it used is 83. That's kind of expensive, but here you can buy new for 44 bucks, or 29 for a cheaper one. It's not necessarily new. So not expensive if you want to have a printed version of it. How do I get rid of this dumb thing? Goodness, it's annoying. Okay. So there's your textbook, and there's other ways to access the textbook as well. I'll show you later, hopefully here. Class videos I've already showed you, then chapter subject videos. So OpenStax actually has created a YouTube channel of different videos to explain concepts, to show examples of problems and things like this. And each chapter, from chapter 2 all the way through chapter 25, have these videos, and so I've provided a link to that site as well. And we will use those from time to time if I remember. Sometimes I often forget that they're there, but we will try to use them. Then up at the top here we have the calendar. I would highly recommend you get comfortable using the calendar because it's kind of a shortcut to everything. In the calendar here you can see that today we've got this homework assignment, chapter 1, apparently due, not today, tomorrow. It's Wednesday. And it's got 15 problems in it, and it's nothing very difficult. It's just some basic things to remember how to do, like converting things and orders of magnitude, and the SI system, which is called the metric system, right? The people call it the metric system. And you can see here that there are these different problems you can click on, and you've got different types of problems as well. You've got some multiple choice problems. You've got some fill in the blank problems, put in a number kind of problems. You've got, what other kinds of problems do we have here? You've got some kind of matching problems here. Ranking problems is what that one is. You've got some problems that have imagery in them. You've also got some problems with video attached to them that you can use, and this video will sometimes give you some help. Some of them have a button attached to a book that can help you to read about what you need to do. In this case, it doesn't connect to our physics book. It actually connects to a different book that is about this particular math problem, and so on and so forth. So especially in this first chapter, it doesn't necessarily connect to our physics book because this is more like a review chapter of math and science concepts rather than actual physics. But the calendar can take you directly to these directly to these assignments. And then here on Saturday we have chapter 2. We're going to try to crank out 2 chapters in this first week because they're both kind of a little bit less challenging than other chapters that we'll see. In this one we're talking about movement of objects, displacement and position, and basic things like average velocity and things like this. So the calendar takes you to those pretty quickly and pretty easily. You can see here that I've kind of got this week a little bit off kilter with a homework assignment due tomorrow and one due Saturday. And then we've got a bunch of homework assignments now afterwards on Fridays. And I think that's pretty much how it's going to go the rest of the semester. We have our first exam starting on the 19th, ending on the 19th of September. You can take an exam anytime you want before its due date, up until its due date. And there's also a due time for the exam. So if I click on this exam here, it shows up down here that it's due on the 19th and at 8 p.m. So you have to finish it before 8 p.m. You will have to take this exam with a proctor. Somebody's going to have to type in a password for you. That password will be given to a proctor. That proctor can be somebody here at the college. It can be me, in fact. It could be Micah Marvin at McCook. It can be somebody in the library or the Success Center. But you have to tell me who your proctor is going to be so that I can send them the instructions and the passwords. And the reason I set it up for 8 p.m. is because, like, for example, the library is open until later in the evening. But Success Center, you have to be aware, is not. Success Center closes most days at like 5 or something. I think Tuesdays or Thursdays it's open late or something. But it has different hours. So you have to be aware of the hours and plan accordingly to take the exams. And you should usually plan at least a couple of hours to take your exam. I usually say plan 3 hours to take your exam. Usually it takes less than 2 hours for exams, but you never know how it's going to go, so you want to have that extra time. I think the exams are timed for a certain amount of, I can't remember exactly what they're timed for, but should check that. I think they're timed for 2 or 3 hours or something like that. So, but if you go overtime, it doesn't count against you. It's just a timer that I put on there so you can kind of know how long you've been working on an exam. Okay. Let's see, what else? I guess that's about everything that we've got so far to talk to. Oh, they have forums up here, but I don't necessarily use the forums thing here. You can create a forum, I believe, as a student, so that you can ask questions, you know, from McCook to North Platte or whatever else, or students that you don't have much contact with. You're welcome to use this area if you want to. If it's not working, I'll help you to make it work. I've not really had any students that have made use of it yet, so I've just kind of stopped thinking about it. But if you want to, feel free to tell me, and we'll get it running for you and everything else. Then the messages area, I will use my Open Math to send messages, and so will you. For example, when you go to a homework assignment, let's go to chapter 1 here. You have this little button here at the bottom of the thing that says message instructor about this question. And it's going to open up this little message box, like an email box. But the great thing about this message box is you can actually put math into this and images into this, and it will bring the question into it and all the imagery with the question into it. So you can do math. So over here, if you press this button here, you can put in something like, let's say x equals 7 divided by x squared plus 4 minus the log. Where's my G? There you go. Log of y, like this. And then when you come out of it, it actually shows you the mathematics, right? So that's a very useful feature. So you can send me math, I can send you back math, you can insert images, you can put in links, you can attach things here. You can also put in a graph or a table. So if I put in a table of things, you can enter numbers into the table. You can create a graph here of some equation or something, and then you can insert that in there. It's very useful for communicating math and physics and science and things. So make use of it. If you have a question about a problem, use this. Don't send me an email. Use this, because then I can actually see what you've been doing so far. I can see the answers you've entered, and sometimes just from the answers you've entered, in fact most of the time, just from the answers you entered, I can see what your mistake is. But if you send me an email, I have to send it back and say, what problem are you doing? Because you usually don't tell me which problem. And then I have to say, what was your problem with that? What was your concern with that problem? Then I have to go through my Open Math and try to find that problem and see what you did wrong. It's just much faster, much easier for everyone involved for you to use the message instructor about this problem button. And every problem in every chapter will have that button at the bottom of it, so that you can just push it and it links me directly to that homework problem. So, in all of these, you may have noticed or may not have noticed, on this left side here, you've got these numbers here. These numbers tell you whether or not you've gotten something correct. You get points here, 0 out of 1 point here. Notice this has 6 things to enter in for only 1 point. You might think, I deserve more points for putting in 6 things. But also remember that you're going to lose fewer points if you miss something as well. So these 6 boxes will each count 1/6 of 1 point. So about 0.16 points for each one of those. And if you get 3 of them right, you'll get 0.5 out of 1. And it will calculate it that way. And if you need to come back and try it again, you can. You have 7 attempts. It tells you this is attempt 1 of 7. Don't get to your 6th attempt without messaging me, please. You know, if you're at 5 attempts and you're still struggling with a problem, definitely message me and move on. Don't beat your head against the wall. The thing that you'll find is that this, if you've never used one of these systems, who has used an online system for homework before? A couple of you? Has anybody in McCook used an online system for homework before?
Yeah.
Yeah? So how many of you kind of got addicted to that getting the problem right? And there's usually like a little green check mark or a smiley face or something. You get addicted to it. It's kind of weird. And when I first used this, I discovered that right away. That students could not let it go. They're like, I gotta get the green check mark. And that's when I knew that I had to use these forever. Because it's so hard to get students to actually care about getting their homework right. Usually they just turn in their homework and like, whatever, give it back to them, they never look at it again, right? But here they constantly want to get that green check mark. And I don't care if it's some kind of psychosomatic addiction. It doesn't matter to me. I don't care at all. If students are interested in their homework, that's fine by me. So you'll find that it is that way and you'll get obsessed over it. But don't obsess so much that you use all 7 of your attempts. Because then I have to go in and reset the dumb problem, and then you forget what you've done before and all this stuff. I'm not opposed to resetting a problem to let you have more attempts, but I prefer you don't bang your head against the wall so much your blood coming out of your ears, okay? I want you to actually learn something instead of just hate me and hate this system and hate this class. So at 5 or before, hit the message instructor button, please, and I will help you out with it. And sometimes it's just a computer problem. This is not a perfect system by any means. It's a free system, which means that everybody that's working on it is working on it on their own free time, myself included. I'm submitting problems to this system as well. They're not charging anybody to use it, and they're not paying anybody to maintain it. So it's definitely not perfect. There will be mistakes. If you find a mistake, tell me. We'll try to go in and fix it right away. Yes, sir.
With our previous attempts, if we message you, we'll be able to see everything.
Yes, I'll be able to see everything that you've done up to that point. So, and that's helpful. It's also helpful, every once in a while I get a student that tries to fool me and says, I've tried this 5 times and I've gotten it wrong every time, but I'm sure I'm right. And I'm like, you haven't submitted one. What are you talking about? I can even tell when you've logged in. If you've successfully logged in, like I have students every once in a while, it's like, I've logged into this homework like 8 times, and every time I submit it, it erases my page and pretends I wasn't even there. And I'm like, I can actually tell if you actually signed into the website. If you never succeeded in signing into the website, you never saw the homework. I guarantee it. So, yeah, I can see everything that you do on this. There's no privacy with the instructor on this website, unfortunately, for you all. Okay, so any questions in McCook? I know I'm just rattling on. This is just the way it is when we're doing this introduction to the class thing. Are those questions, or are you guys just talking to each other? I can't hear you, sorry?
That's outside.
Oh, that's outside. That's no good. All right, what time is it anyway? We're 10:12. What time are we done here? Or 10? 9 o'clock's not working. We're done in here at 10:30? 10:40? 10:40. Okay, so we got a little bit of time. All right, so let's go back to where we were here. So chapter 1. As you can see here, chapter 1 homework assignment has got some conversion things, got a little bit of math, and there's some trigonometry problem down here. I know that maybe 1 or 2 people in the class have never taken trigonometry. That's not a huge problem because I will teach you as much as I can about trigonometry in this class, and you'll use it enough that you'll trying to just kind of learn what you need to learn. Trigonometry as a course is kind of different than the trigonometry we use in this class. We use some very basic principles of trigonometry in this class, and we don't really delve very deeply into the laws and the proofs and all the mumbo jumbo that you learn there. Some of the things that we're going to talk about here are scientific notation and orders of magnitude and metric system, of course, and just physics in general. And without further ado, we're just going to go ahead and get started because you got some things to do. We will meet again on Thursday, like I mentioned, and record that class for those who can't make it. But let's go ahead and talk about Chapter 1. Yes, sir? So tomorrow we will not meet. We will just meet on Thursday. Okay? Let's see, did I close my other link to this book? I guess I did. Takes some time to connect to this book sometimes, especially with the internet in this building. It's sometimes really lacking. Yes, I will record the class Thursday, but send me an email, please, just so I remember. All right, come on, book. Open up here. What's going on? I really despise this internet here. All right, I might have to just go. I do have a saved version of it somewhere. Let me find it. It's in my downloads, I think. Where are my downloads? Maybe. There it is. Okay. All right, now we're talking. Let's go to page 1. Where's pages? I hate this. How do I do this? How do I go to? I can't see anything. Good night. How do I go to a different page on this? I'll just search it. College Physics, page 13, page 17, chapter 1. There we go. Okay. Okay, so now, how do I get rid of this thing? Search. I have no idea how to get rid of that thing. All right, so let's go ahead and get started. I am going to pretty much, we're going to have our discussions with the book up on the overhead. I'm not going to give you any slides or anything besides this because I want you to see what is in the book for the things that we're talking about. I don't want you to have to try to correlate your book with my discussions. How do I get rid of this? I want to just get rid of this thing. Done. There we go. Okay. So let's go ahead and start talking about Chapter 1. We've already talked a little bit about what physics is. Physics is the study of nature, and it covers a lot of different things. Already, as we've kind of zoomed through here, or scrolled through here, we've seen a picture of a nebula. We've seen a picture of a crane, a sandhill crane, I think. So that even makes it more apt. Nope, that's a Canadian goose. Never mind. Not a sandhill crane. We see a picture here of an iPhone, very early version of iPhone, a microwave. Here's a great one. I love this picture of this this slice from a X-ray, and this biological slice of cells. All of these things are related to physics. In fact, there is no science that isn't related to physics, even mathematics. A lot of people like to say, well, mathematics is the pure science because all sciences depend on it. Well, guess what? Physicists invented mathematics to describe physics. So actually, it's the other way around. There's hardly any mathematical concept that wasn't invented by a physicist at some point. And so we also have these famous figures in physics, from one of the most famous in Isaac Newton to one that is a little bit less famous, but quite famous in her own right because she did so much for women in physics and women in science in general, and that is Marie Curie. Marie Curie. Her name is not pronounced that way at all because She was from Belgium or France or something like that, but anyway, it's good enough. She was around about the same time as Einstein, and Isaac Newton, of course, was hundreds of years ago. But we have so many different things going on in physics, both on the side of the actual science and on the side of history. History and science, and particularly history and physics, are so entangled with each other that you just cannot separate them. And so we generally try to teach physics from a historical point of view. And we start off with some of the more basic concepts, the first things that were discovered and the first things that were studied in physics, and move through time studying them. We also have things that you can't even see that we study in physics. For example, this is a demonstration or a model of what an atom is represented as. I mean, it's not really what it is. It's not what it looks like by any means. We have no idea what an atom looks like. There's no way to look at an atom. It's impossible. It's not just difficult. It is literally impossible. There is no way to do it. And so we'll never see an atom, ever. The light that we see with is much, 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 thousands of times bigger than the atom itself. So how could we see the atom with the light that we see? We can definitely make representations. We can make a detection. We can detect an atom, but we cannot ever see them. So we start off with how physicists do science. How is science different with physics? I've already mentioned the fact that we don't really ascribe to this idea of the scientific method so much as other scientists do, or we do, but we do it in a very different way. We tend to think in terms of what we call models, theories, and laws. And so that's why this is put in here, of course, models, theories, and laws. What is a model? Well, a model is what physicists do. It's kind of like this representation that they make, using usually mathematics, maybe sometimes graphical representations like pictures, graphs, whatever, to describe what is happening and why it's happening, to try to explain what is happening. Now, are these models always correct? Absolutely not. They're not always correct. In fact, more often than not, they're incorrect. So the model, in physics, a model is very much like the hypothesis in the scientific method that you've probably been taught. The model is more like this is what we think is happening. This is why we think it's happening, is a better way to say that. And then we test that model by making observations, doing experiments and things like this. And then we try to modify that model to fit what we see. And that's where we really kind of diverge from many of the other scientific processes out there. Laws are the things that we observe in nature that are always the same every time. So there used to be a law in physics that is no longer a law in physics. Newton changed the law. The law was given by somebody, I don't remember who, but a law was said that things always fall down, right? When you drop something, it falls down. And Newton changed that. He said, no, that's not true. Gravity doesn't work that way. Newton said gravity makes things that have mass attract each other. And since the Earth has so much mass, everything that's near the Earth always falls towards the Earth, but that's not down. That's just towards the Earth, right? Jupiter is not falling down. It's moving around the sun because the sun is pulling it towards the sun. And because it has this orbit, every time Jupiter gets pulled towards the sun, it gets pulled into this circular orbit that it lives in, right? So that was a law that was changed. The law of gravity has been changed again since then, in fact. Einstein said Newton's wrong. Gravity doesn't pull on things because there's two masses and they just attract each other. Newton said something completely different. I mean, Einstein said something completely different. Einstein said mass actually warps the fabric of space-time. You may have heard that word before, space-time. It says it actually warps the space-time continuum, and that all things have to travel along the space-time continuum. And so when you have these bends, things fall into these warpings, and then you don't have to understand all that. It's just you need to know that models are not necessarily things that are always the same, and laws are not always the same. There's something that we change as we see them change. If we see a change, then we change the law. And eventually we've come down to these laws that haven't been changed in a long time. And we call them fundamental laws. And we have many of them, and we'll learn many of them. Okay, well, we don't have many, we have a few. But fundamental laws are really the things that physicists are looking for. We're looking for the things in the universe that we observe that never change. They always work this way every time, because then if we understand what those are, we can use them to try to understand why other things happen. Laws, usually we don't understand why they happen. We just observe that they always happen this way. Usually there's almost no way to actually understand why they happen. We just see that they're happening this way. So, and then you have theories. Once you have a model that starts to become very well established, and you start to create mathematical understanding from it, and the laws that you understand can be used to describe why this model is working. Once you get these things all working together and it looks like it's pretty established, then it starts to become a theory. Okay? Theory can also be used as kind of like this idea of the conjecture, or an idea of why something works that needs to be tested. So you take some observations and you create a theory on why they're doing what they're doing, and then you can test that. So that's very similar to a hypothesis, but it is fundamentally different in many ways as well. But this is more of the scientific method that we follow as physicists, where we observe nature around us, and the things that we observe, we make laws from them, models from them, and theories from them, and then we try to test these things for errors. We're looking for the problems. We're looking for the weak points. And then those weak points, we change, and we make our theories stronger, and our models stronger, and our laws more correct. Right? This started just so long ago. This is one of my favorite examples here. This is Aristotle. This guy had many things attributed to his name, but he lived about the same time as another guy named Democritus. The Greeks were really great thinkers, and so they came up with a lot of theories from the laws that they observed in nature. Some of them good theories, some of them bad, but Democritus came up with one that was brilliant. He said, if you take a rock and you smash it, what happens? What happens to a rock if you smash it? It breaks apart, and you have a bunch of little rocks, right? What if you break all those rocks? Okay? So what happens if you do that ad nauseum? Do it until you're just sick of doing it. Eventually, what will happen if you do that forever? What will happen? Get smaller and smaller bits. Will there ever be an end to it? Can you just get smaller and smaller and smaller forever? So we have some people saying yes, some people saying no, some people saying maybe. Democritus said, eventually you will get to a rock that you cannot break. He suspected that the universe was made of tiny little particles that could not be broken. At some point there was a particle that was so small that it could not be broken into any smaller pieces. And you know what he called this piece? You know what he called this little rock? He called it the atom. So at 2,000 plus years ago, some guy came along and said, I'll bet you there's a small particle out there that can't be broken. I'm going to call it an atom. And guess what we call small particles today that are difficult to break? We call them atoms. They're not impossible to break. Atoms can be broken. We've discovered that. And we've discovered that even the particles that atoms are made of are not the smallest particles, that even those particles can be broken. However, that's still pretty amazing for a guy to think of that he had so little evidence to go on. He had so few experiments to move on from there. But it was a brilliant use of logic. You have Galileo here, another great scientist. He's one of the ones that did a lot of experience with astronomy. He was the one that dropped the bowling balls or the lawn bowling balls, whatever, out of the Leaning Tower of Pisa, and discovered that gravity pulls with the same amount of gravity accelerates all objects no matter what their mass at the same rate, right? And it was later on that it was Newton that said gravity actually pulls on those objects with different amounts of force, but it's the same acceleration because it is proportional to the mass, right? So bigger masses get pulled more, which accelerates them the same. And you have Niels Bohr here. Niels Bohr was a scientist in, ooh, that was, what happened? Here we go. Niels Bohr, here is a scientist in the 20th century, late 1800s. He was a young man, and in the 20th century he made his mark on physics by creating the new idea of what an atom is, and starting the modern understanding of what atoms and particles are all about. One of the fathers of quantum mechanics. And now we've got scientists and equipment that can do something like this. This is an image from a scanning tunneling microscope. And a scanning tunneling microscope looks a lot like a little record player. It has a little arm on it with a little needle on it, and you put a piece of material and the needle scans across the material. But the needle point is almost the size of an atom. The point of the needle is just a couple of nanometers across, not very big. And if you're not aware, an atom is about a tenth of a nanometer, so about a hundredth of a nanometer is about the size of an atom. So the tip is, just a few hundred atoms wide. So it's so sharp and so tiny that it actually can detect atoms. When it gets close to an atom, it actually bumps. It actually gets bumped a little bit. And there's a laser on the back of that arm that detects that bump and creates this image. This is not a picture of atoms, but each one of these little dots is a representation. Each one of these little dots in here is a representation of a single gold atom in a sheet of gold. So that's kind of, we've come a long way. We've done a lot of things in physics. There's a lot of interesting things going on. I want to stop talking about science for a second and talk about social science for just a minute. This image is one of the most influential images in the history of mankind. This image was taken probably, I think this one was from the first trip around the moon, Apollo 8. So it's probably 1969 maybe or something like this. And as they were coming around the moon, the dark side of the moon, they experienced the moon rise, the Earth rise rather, right? The Earth rise over the moon's horizon. And they sent this image back to Earth live, and people all over the world were watching it. Something like 4 billion people were watching this image come live from the Apollo 8 mission, the Apollo 8 capsule. And as the world saw this, I think it was 68, actually, 1968. It's just before 1967. As the world saw this picture, they saw the Earth as they'd never seen it before, as just this tiny little blue marble out in this huge expanse of space. And does anybody know what happened in 1969? In 1969, the civil rights movement exploded. People started to say, you know what, we need to stop discriminating. We need to stop putting down people of race. We need to stop putting down the female half of this world. We need to stop. People started standing up for the rights, and other people started to support the movements. Okay? There were huge wars going on at this time. The Vietnam War being the biggest among them at the time, but there were others that were just as big. There were others almost as big. Vietnam, in that whole region, there were wars going on all over that region. There was in Burma and other places, there were just terrible things going on. The Middle East, there were wars going on in the Middle East all over the place. We were on the brink of nuclear warfare at that time. It was the height of the Cold War. And it didn't take much longer before the United States pulled out of Vietnam. Just a couple more years. They're like, we can't sustain this anymore. We cannot just go fight people because they happen to have a communist government. That's the only reason we were fighting them. There was no other reason. Just because they decided to follow one political leaning and we followed a different one. The same thing happened in other places. People just started thinking, maybe this is not as important as they thought it was after they saw this picture. This was a hugely influential picture. And social scientists do studies about this single picture making huge changes in the world, changing people's mindset, just by helping them to understand that, hey, we're kind of alone out here on this planet. Maybe we ought not to try to kill each other so much. And I really think it's gone downhill since we haven't been to the moon. Don't you think? The 70s weren't the best decade of all time. There's no doubt about it. But certainly we're not doing much better now in the 2010s, 2010s. We're still struggling with a lot of these things again. And I think it's time that we get out there and start seeing that there's something bigger than us and more important than us probably out there in the universe. This is what science can do to the world. Science is so much bigger than the world. And we saw that with the Apollo mission, and we haven't left our planet since. We haven't even come close. The space shuttle never even got out of orbit. Okay, and the space station's even closer to the Earth. So we're just not doing it. We need to go to Mars. We need to get out of here. We need to get out of our world and start to look back on it and say, you know what? That really is kind of a good place. We need to take care of it. We need to take care of each other. Because Mars sucks. Because whoever goes there is gonna die. There's no question. The first people that go to Mars will die on Mars or on the way. It's just without a doubt, it's gonna happen. And people are gonna realize, hey, this may be worth doing, but there's other things here worth doing even more. And it may take some deaths on the way to Mars to do it. So anyway, that's my social science for the day. Now you've got your general education for this class. Okay, in the physics world, we use the SI system, Système International. It's French for the international system. And so they call it the SI unit. They call it SI units, also known as metric units. So for length, we use the meter. For mass, we use the kilogram. Some people say, why don't you use the gram? I say, I don't know. We don't. We use the kilogram. And for time, we use seconds. Electric current, we use the ampere. And we have many other units that come from these units, that are derived from these units. And so we will learn about many of these during this class. Here's a great example of this. You may not have ever seen an atomic clock before, but this is what is called an atomic fountain clock. This is the one that is in, I think this is the one that's in Colorado, actually. But an atomic clock, what it does is it uses vibrating cesium atoms to set what they do is they actually tune a laser, they tune a microwave laser to the vibration of cesium atoms so that it's making the atoms vibrate at exactly a particular transition. The vibration of that transition is known. In other words, the frequency of that transition is well known. And then they use that frequency of that laser to be the tick, tick, tick for a clock. And then you have an extremely accurate clock because that frequency is quite a high frequency. It's something like something times 10 to the 15 hertz or something like this. Extremely high frequency, so it's like having a clock that ticks 10 to the 15 times per second. So you have a lot of precision there. Why do we care about the clock being so precise? If your clock is precise, every measurement that you make that involves time can be that precise. So you can know the speed of something to a very, very high precision. You can understand when something arrived somewhere to a very, very high precision. Because we're looking for very, very high precision, we've stopped using physical objects to measure things like the meter. Right? The meter used to be defined by a rod that was, we called it 1 meter. But the problem is a rod made of metal or just about any other material really shrinks and lengthens with temperature. So it had to be kept in a temperature-controlled environment. Well, how do you control that temperature? Well, you have to control that with something else. Everything had to be controlled. And so now they actually use the distance that light travels in one 299 millionth of a second is now the definition of a meter. So they're using light because light is a constant. One of those things that we've discovered over time in physics. Kilogram has also been defined, has been defined using a physical object for many, many years. There's a platinum iridium cylinder kept in France somewhere, or England or somewhere like this. It's actually in Paris, it looks like. But they stopped using that just recently. Now they're using a different measurement that involves, again, light and time, actually. So we know how much these things are, and we have standards for them, but the standards are getting better and better. Metric prefixes. This is something we've got to cover really quick. We've got 1 minute left. So the metric prefixes are all these things like the giga and the mega and the kilo and the deci and the centimeter and the millimeter, millisecond, whatever. It's all these prefixes on the beginning of words that mean something, and this table tells you what they mean. They either mean it's 1/10 of something or a million of something or whatever. And these things are all, there's a lot of these things. We don't use them all. The ones we generally use are like giga, mega, kilo, and then centim, milli, and micro, and nano. So we don't use them all. We just use about half of them maybe that are there. Unit conversion is the last thing. If you've not done unit conversion in a while, I recommend highly that you use this method of this fraction method. So if you have 80 meters that you need to convert into kilometers, it's 80 times 1 kilometer per 1,000 meters, because there's 1 kilometer in 1,000 meters. You use this fraction, which is essentially the number 1, because 1 kilometer is equal to 1,000 meters, and then you cancel out your meters. If this is not easy for you, use this method. And there are some videos about this in the video section, and there's videos all over YouTube about this if you're struggling with it. And send me an email. If any of, don't be embarrassed if you don't remember these things, or if any of these things are just kind of new to you or whatever. Get help from me right away. We're not going to have time to go through the examples, but we'll go through them. If you need me to go through them on Thursday, I will. But I would like you to try to get this homework done by tomorrow, if you can. Send me an email, give me a call if you need help. Get help from your classmates, set up a study group. And that's all I have for you today. We'll see you guys Thursday. And if you guys want to study, I don't know if you want to study in like right after this class every day or something, you're welcome to do that. I'll leave this classroom open for that if you want to do that. So that's fine. We'll see you guys in McCook on Thursday. What's that?
Do you want that paper emailed to you by tomorrow?
Just sometime this week is fine. Yeah, don't forget your paper about the physics magazine. Grab a physics magazine if you don't have one. I've got some in the next room as well.
And
You need to grab one.
do 30
Just